So hello everyone and welcome back to this next lecture in the DC-DC converter series, and this is where we had left off in the previous lecture where we were running the flyback converter. So specifically, if we go to the circuit, the difference was in changing the polarity of the secondary winding of the transformer. So we had reversed the polarity. So if there's a dot polarity in the primary on the top terminal, the dot polarity on the secondary is at the bottom terminal. So this is essentially the trick in the flyback converter, that it allows the primary to take energy from the source when the switch is turned on, and when the switch is turned off, the energy in the transformer, the magnetic energy stored in the magnetic field in the transformer, is discharged through the secondary to the load. So in essence, this is where we had left off. The only problem was that we saw that there was still an instability problem. So in this lecture, we are going to solve this instability problem. So this is where we had left off. And as you can see, when there is a change in the switching, this entire switching cycle, rather the entire simulation, tends to become unstable. Though it is not completely unstable, it is largely oscillatory. So we'll try to figure it out in this lecture. So let's go back to the web browser. And as always, before starting this lecture, a little bit of brief background, that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length online courses on the MOOC website Udemy, and this is the very first course that I created, which is simulating power electronic circuits using Python. In this course, I talk about the basics of Python programming, how to install Python power electronics, some basics of power electronics and circuit theory, and finally there is a case study of how to simulate a buck converter. If, however, you are interested more on the signal processing side, I have another course which is Basics of Digital Signal Processing for Power Engineers, and in this I talk about the basics of signal processing, how signal processing is applied to electrical engineering and to circuits, and finally there is a case study of how you can design and implement a low pass filter and a notch filter using Python packages such as NumPy and SciPy. And the third and the latest course which I created is Simulation of Magnetics for Power Electronics using Python. And in this course, I talk about the basics of magnetic elements, how to model magnetic components like inductors, coupled inductors, and transformers using Python and Python Power Electronics. And finally, there is a case study of how to simulate a flyback converter. So the links for these courses is provided in the description for this video. So if you are interested, please do check it out. So coming back to the main lecture. Now, in this lecture, let's go back and have a look at our simulations. So we saw that there is an oscillation. So for example, we see that this happens at 0.001, and that's no real surprise. All we have to do is go back and have a look at our gate signal. And in this gate signal, you see that the modulation is 0.1. So therefore, it is only natural that at 0.1, which is 10% of the switching cycle, we see this oscillation. So what exactly happens? In the beginning, the switch is turned on. So therefore, you see that there is, actually I'm looking at the output voltage. Let me go and look at the winding voltages. This is the winding voltage. Yeah. So in the winding voltage, as you can see, when the switch is turned on, the blue line is 24 volts because we have considered a 24 volt input DC, which corresponds to like a 24 volt battery. And the output is 12 volts because we have a 2:1 transformer. When the switch is turned off, this entire system starts becoming extremely oscillatory. Alright. So let's try to figure this out. Before that, let's go and plot a very, very small portion of this. So I'm going to go back here. And in this winding, I'm going to plot, actually let me just plot 1.0 e raised to minus 6. Oh no, actually. Let me plot this. And let me plot this. So this is a very small time period. I just want to look at the exact nature of the waveform in this very short period of time. So as you can see, there is some amount of oscillation. The oscillation tends to die down, right? So we see that there is an oscillation. Now if we come back and have a look, we see here that this oscillation also tends to be a little sustained. right? Now, this is one of the biggest problems with simulating magnetic components, and that is in dealing with the oscillations in the circuit. Particularly when you're dealing with magnetic components, it's all about how you deal with the magnetic energy stored in these components. For example, you have a transformer, you have an inductor, you have a coupled inductor. This energy stored in these windings, in the inductance of these windings, will need to be dealt with effectively. Now, the way we have simulated, rather modeled this in these inductors, that is these two windings, is as a voltage source in series with the resistance, right? So all we are doing is we are calculating the current and we are adjusting our voltage source and our variable resistance so that we achieve a certain current, right? Now, the only problem with this is that we are doing all our loss modeling, everything in this one resistor, right? Now, the problem with this kind of a modeling is that this does not capture the core losses and the eddy current losses in the transformer, which is not really so much dependent on the current, but rather on the voltage, right? As you might know, there are different components in the transformer losses. There is the ohmic losses, that is the I square R losses, and there are the eddy current losses and the hysteresis losses. The hysteresis and the eddy current losses are core losses which are dependent on the voltage applied to the winding. So really speaking, it is a little difficult to just use only one resistor, and that's essentially the problem which I'm doing right now. Now, how do we solve this? We should, if we can emulate some of the core losses, that should reduce the burden of this variable resistor and also add a little bit of damping to the circuit. Because remember, when you look at this, these oscillations are generally when the simulation is struggling to actually settle down. And this will improve if we add a little bit of damping to our circuit. So how would we do that? We do that by connecting a resistor across this, also a variable resistor, and this variable resistor will be adjusted to signify the core losses in the transformer. So let me do that. So I'm just going to come add a branch, delete an element, and copy this, and let me give it another name. I just realized I made a spelling mistake, but I'll leave it as it is. Let me call this the loss, right? So this is specifically modeling the loss in the transformer winding, right? Now, let me come over here and do the same for the secondary winding as well. I will delete an element and copy this, and I just have to add loss. So I have now added two resistors that are variable resistors that signify the loss in the transformer winding. So as always, since we made a change, we have to go back and process the circuit schematic. So let me click on process circuit schematics. And it's good, there are no detectable errors. Let's go to the parameters, two winding transformer. We just have to change the parameters of the transformer. So as you can see, this is a new one which we've added, right? So there is a variable resistor, right? It is, we can give, the name is winding 1 transformer 1 loss. We can leave it as it is, or you can name it something else. So for example, we can call this XMR1 mag loss, right? This is a transformer, rather actually call it XMR1 winding 1 magnetic loss, right? And the initial value of the resistor can remain the same. The control tag is just a unique identifier. As long as you know what this signifies, that's good enough. We will change the value of this in the actual control code. So we now come back to the second one, that is this one. Let's also give it a name, and we can also call this transformer winding 2 transformer 1 mag loss, right? You can change it to whatever you want, not a problem. The initial value can be 100. So with this, we've added the two loss components. Now let's go back to our control, and our control, our transformer model, now has to reflect these two. So how do we do that? We add a control output. So the first control output will be the winding 1, right? So winding 1, transformer 1 loss, right? Let's click on this and let me call this mag loss 1. Okay, the initial value can be 100. We will set it to an actual value, and let me add the other one. So this is winding 2, transformer 1 loss, and I will call this mag loss 2. Initial value can be 100, and save the output. So with this, we are done configuring it. Now we have to add it to our control code. So let me go over to my code and let me go over to the transform model. So there is one other thing which I noticed. If you look, I have actually given the resistances a hard value, that is 0.01. This is usually never recommended. Let me cut this out from here. Let me go all the way below and let me start defining it. Rather than defining it like this, let me define it as a ratio instead. Alright, so for example, what this means is that, let me say that just like we defined this ratio, we can say that we will define, or rather it's better this way, because this is a leakage inductance. We will say that this resistance should be such that if the rated current flows through this resistance, the drop would be something like, let's say, 0.2%, right? And this is a very, I think, reasonable value. It is better to calculate it like this than to give a steady number, because as the rating of the transformer changes, things do change. At least the resistances have to reflect on the ratings rather than be constant values. Now, we now have to give the other winding as well. So for that, what I will do, I will just copy this and let me call this, what do I call this? Mag loss. And here I will call this core loss representation. Right? Now, how do we do this? This would be a little different. This would be something like this, right? Because now what we're trying to say is, if the rated voltage is applied across this current, right? So it's something like this. That is, let me first change this, mag loss 1. So we are going to say that if V rated or V1 rated is applied across mag loss 1, so that is mag loss 1. In that case, the current that flows should be a very small percentage of the rated current. So that means this should be, I would say, a safe value should be around, I think around 2% also, maybe a little different, or 0.2%. Typically the losses in a transformer might be in the range of even a little more, so maybe we can actually give it a 1% loss, right? That is, if the current flows, that is, if rated voltage is applied across the winding, a 1% loss current will flow across this loss winding, right? Maybe that is a little high. Let me change this to 0.5%, right? So this has to be 0.5 times the rated current, right? Now, what that means is, we now have to say mag loss 1, I'm just rearranging, and put a bracket here. So it's very similar to this formula. I'm just trying to write it so that it's obvious. Let me copy this, put mag loss 2, V2 rated, and I2 rated, and I delete this. So now we have inserted a loss component. Let me just go and make sure that I have the value right. I usually copy the variable, but this time I didn't. Mag loss 1, mag loss 2. Yeah, sounds okay. So let me make sure I saved my file. Yes, I did. So the rest seems okay. Let's run this and have a look. So always make sure that we go and have a look at the command console, make sure there is no error. There is none. So the simulation is indeed running. So with this, let's go and plot the winding voltage. And you see something very different, right? You see now the oscillation does not happen. There is no oscillation, right? Instead, you see a very different kind of waveform. It is now stable, though there is an overshoot. We'll talk about this very soon. Let me plot the output voltage. And the output voltage is also stable, right? Of course, this is the orange line is the actual output voltage at the end across the capacitor, the filter capacitor. This is going to rise very slowly, which is why it's still 0. The secondary voltage is what is actually applied across the secondary of the winding. So this is a switched waveform, which is the reason why you see this, right? So with this result, now let us go and have a look at our winding voltages again, because now we should have a few more cycles. Well, we still don't. We have to wait probably for a couple of more seconds. But now you see, most importantly, the oscillations have died down, right? So when the switch is on, we see the usual behavior. That is, the primary voltage is 24 volts. Secondary voltage is 12 volts. When the switch is turned off, you see here that the voltages are now 0, right? Voltages are now 0. Now, let's go back here and click on the winding voltage. So there is another issue, and I'll talk about that very soon. So here you see the winding voltages. This shows you exactly the behavior of the flyback transformer. So when you see that the voltage indeed is 24 volts and is 12 volts, right? This is when this transformer is now turned on, the primary is charging, right? Both, that is, the input DC voltage is charging the primary, right? Now voltage appears across the secondary. However, that voltage should not do anything, and that's what we'll do when we start analyzing the currents as well. When the switch is turned off, the voltage across the primary is 0, right? Now the voltage across the secondary is also 0. Now this might come as a surprise to you, because at this point you might think that the secondary is indeed conducting, right? The secondary is indeed conducting. But it's important to understand that the way it works in the simulation, this is, however, not a voltage that is a voltage, physical voltage that appears, but rather this is the discharge of the induced EMF, right? So let's keep going. And let me plot the output voltage again. So you do see that this voltage is now reasonably stable, right? And if you keep plotting, you'll see that this orange line is gradually increasing, which is why the output voltage is gradually charging, because there is a filter capacitor, it will not charge immediately. So this is now a working simulation, right? This is the flyback converter. Now at this point of time, I will stop this lecture, and because I don't want it getting too long, in the next lecture, now that we have a stable simulation, we will analyze the waveforms of this converter. That is, we'll look at the primary, the secondary, the currents, everything else, right? So as always, if you have any doubts, please do post either in the comments, or send me an email, or message me on social media, whichever is your preference. Otherwise, I will see you next week, where we will continue with the analysis of this converter. So thank you so much for watching, and see you soon. Goodbye for now.